Section 2.7, related rates. If we were pumping air into a balloon, both the volume and the radius of the balloon are increasing, and the rates of increase are related to each other. However, it is much easier to measure directly the rate of increase of the volume than it is of the radius. In all related rates problems, the idea is to compute the rate of change of one quantity in terms of the rate of change in another, which is usually more easily measured. Then we use the chain rule to differentiate both sides with respect to time. Here are the 7 strategies for related rates problems. Number 1, read the problem carefully. 2, draw a diagram if possible. 3, introduce notation. 4, express the given information in terms of derivatives. 5, write an equation that relates the quantities. 6, use the chain rule to differentiate. 7, substitute the given information and solve for the unknown rate. Many times people use the acronym to remember the order, and that's DREADS. Diagram, rates, equation, derivative, and substitution. Substitute and solve. You will never, I repeat, never plug in values before taking the derivative. The substitute, oh, sorry, it's going a little too fast. The substituting happens after you take the derivative. So let's take a look at example 1. A pebble is dropped into a calm pond, causing ripples in the form of concentric circles. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area A of the disturbed water changing? So first, I draw a diagram. So I have a circle with my radius r. Then I need to write out all of the rates, all of the given information. I'm given that the radius is 4 feet. I'm given dr dt, which is the rate at which the radius is increasing, is 1 foot per second. And I want to know the rate that the area is increasing. Next, I need to write an equation that relates all of these items together. Notice I have radius and I have area. So I need an equation that relates radius to area. So that would be area equals pi r squared. Now that I have an equation, I will take the derivative with respect to time. So the derivative of a with respect to time is dA dt. Then I have 2 pi r dr dt. I have taken the derivative with respect to time. Now that I've taken the derivative, I will substitute the values that I have and solve for the unknown. So I know that the radius is 4, so I will plug in 4 for r. I know dr dt is 1, so I will plug in 1 for dr dt. I can simplify and solve for the unknown, and I get that dA dt is 8 pi feet per second. That is my final answer. To help us, I will try to color each step. Diagram, I will try to keep red, rates green, equation blue, derivative purple, substitute and solve in black, and I will box my answers in orange. This is just to help you as we continue through the lecture. Taking a look at problem 2. At noon, ship A is 150 kilometers west of ship B. Ship A is sailing east at 35 kilometers per hour, and ship B is sailing north at 25 kilometers per hour. How fast is the distance between the ships changing at 4 p.m.? So first, I need to draw a diagram. So if this is ship A traveling east, this is ship B traveling north. This distance between them, they told me, was 150 kilometers. There we go, 150 kilometers. So at noon, this is where the ships lie. A is going to continue sailing east at the specified rate, and B will continue sailing north. Now we need to start identifying our rates and setting up our variables. So I will call this Y. This is 150 minus X, and we'll call that Z. The reason I'm doing 150 minus X is we know that ship A is 150 kilometers away. So if X is how far it travels, it will be cutting into the 150 kilometers. I'm going to take the information given. I know that dy dt, the rate that B is going, is 25 kilometers per hour. I know that X, the rate that ship A is going, is 35 kilometers per hour. I also want to find dz dt, and that's how much or what the rate is that the distance between A and B is changing. I'm given that time is 4 because that is 4 hours after noon, and noon was the initial time that they began. Now then, I will write an equation. I need an equation that relates x, y, and z. I notice that this is a right triangle, so I will use the Pythagorean theorem to make my equation. Z squared equals 150x squared plus y squared. Now that I've done that, I need to take a derivative with respect to t. So that's 2z dz dt equals 2. Leave the quantity alone on the inside. Chain rule, multiply by the derivative of the inside. And then plus, don't forget your dx dt, because we took the derivative with respect to x. Then that would be plus 2y dy dt. Notice since we're taking the derivative with respect to t, that every variable that we take the derivative of needs a dz dt, dx dt, or dy dt. Now that I have that, I will plug in values I know. I need to find z. I'm not currently given z, but time is 4. So when time is 4, I'm able to find out what z will be. At 4, x, ship A, traveled 35 kilometers per hour. So after 4 hours, ship A would have traveled 140 kilometers. Do the same thing for y. Y is traveling 25 kilometers per hour. So when 4 hours have elapsed, ship Y has traveled 100 kilometers. This being said, if I solve for z using the Pythagorean theorem, I have 150 minus x squared plus y squared. I will take the values of x and y and plug in so that I can find what z is at 4 o'clock. When I get the square root of 10,100. That is my z value. So I will plug that in as my z value. My dz dt is what I'm trying to solve, so I will leave that alone. And I have 2, still have 150 minus x, which is 10. This 10 is coming from 150 minus 140. I still have the negative 1, and dx dt from the green above was 35 kilometers per hour. Plus, I have 2, y is 100, which I found off to the right. dy dt is 25 kilometers per hour. I tried to color code this for you to make it easier for you to see. Now all we need to do is solve for dz dt. When I do this, I get 4,300 over 2 times the square root of 10,100, which is 215 over the square root of 101, which is approximately 21.4 kilometers per hour. Now, when you're doing WebAssign, you would use a calculator to get the 21.4, and they would tell you how many places to round to. On an exam, you would leave the fraction as is, simply because you're not allowed to use calculators. Let's move on to number 3. Number 3 says, a street light is mounted at the top of a 15-foot tall pole. A man 6 feet tall walks away from the pole with a speed of 5 feet per second along a straight path. How fast is the top of his shadow moving when he is 40 feet from the pole? Not what I wanted. Sorry. There we are. So we need to draw. There's my light pole, and there's my man, and he's walking away. So his shadow formed from the light hitting him would make this triangular pattern. This distance we'll call x. That distance we will call y. I know that the light pole is 15 feet tall, and I know that the man is 6 feet tall. Other rates I know is that dx dt, that's how fast the man is walking away from the light, is equal to 5 feet per second. I also know they want to know when he is 40 feet away. That would be an x value of 40. What I'm trying to find is how the top of his shadow is moving. The top of his shadow would be at the end of x plus y. So the derivative of x plus y with respect to t is what we're trying to solve. So I need to take the derivative, the equation I'm going to use to combine these, or let me step back a little bit. Ultimately, I need to take the derivative of x plus y. First, I need to find an equation that has x plus y. Off to the left, looking at these triangles, I see that they are similar, so I can set up ratios. 15 is to 6, as x plus y is to y. And I'm setting this up with the smaller triangle compared to the bigger triangle. If I simplify this, I get 15y equals 6x plus y, quantity. Ultimately leaving me with y equals 2x over 3. So what happened in that second step, if I lost you, is I distributed the 6, so that would be 6x plus 6y, and then subtracted 6y from both sides. So I know that y is 2x over 3. So I need to take the derivative of x plus y. So that's the derivative with respect to t of x. Y happens to be 2x over 3. If I simplify, that leaves me with 5x over 3. And now I take the derivative with respect to t. So that's 5 over 3 dx dt. I could have put a 1 if I wanted to. The derivative of x is just 1. I then plug in the rate that I was given, which was 5, and I have that the final rate, or the rate at which the shadow is increasing, or that the shadow, is moving away from the pole, is 25 over 3 feet per second. This one's a little bit different than number 2. Number 2, we used implicit differentiation by taking the derivative of both sides. In number 3, our equation was just x plus y, so we could just take the derivative straight away. We used similar triangles to help us solve for y. Let's move on. Let's take a look at another example. Number 4. Gravel is being dumped from a conveyor belt at a rate of 30 feet cubed per minute, and its coarseness is such that it forms a pile in the shape of a cone whose base diameter and height are always equal. How fast is the height of the pole increasing when the pile is 10 feet high? So what we're going to do first is draw a picture. So here is my cone. And as I start to define the variables, they tell me that the volume is 30 feet cubed per minute. That's how fast it's being dumped. So that's how much is going into the volume of this pile. They also tell us that the height and the base are always equal. So if my height is h, then my diameter of the base would be h as well. So the radius would be h over 2, which is what I drew on the diagram. They also ask me when the height is 10 feet. They want to know how fast the height, so dh dt, is increasing. So we need an equation that relates volume to height. Volume of a cone is volume equals 1/3 pi r squared, h. I plug in the values. 1/3 pi r is h over 2. Then I have the squared and the h. I simplify further just to make it simpler when I'm finding the derivative. And if you're wondering where the h cubed came from, I have the h squared times another h. That's where the h cubed is coming from. We'll come up here to find our derivative. I'm going to take the derivative of both sides. When I take the derivative of the left side, I get dv dt. When I take the derivative of the right side, 3 comes down, so that's 3 pi over 12. H goes to the power of 2, and I need my dh dt. Now that I've taken the derivative, I will then substitute and solve. So I'm changing dv dt, they told us was 30. We have 3 pi over 12. H, they tell us, is 10. And then we have dh dt. I need to solve now for dh dt because that's what the question is asking us for. So that's 25 pi dh dt and then I divide, and I get that dH dt is 30 over 25 pi, which simplifies to 6 over 5 pi feet per minute. And that would be our final answer for number 4.